Hi. In this video I'll discuss the basic inputs and outputs of the analog computer. By basic inputs and outputs, I basically just mean the inputs and outputs that are included with any general purpose analog computer. I'll be demonstrating the Comdyna GP-6, which has these inputs and outputs. Analog computers, like any type of computer, are used to solve problems. So we need a way to input the parameters of the problem and obtain the results. The analog computer can solve a wide variety of problems, but it's most suited to solve differential equations. If you're not familiar with differential equations, you might still find this video interesting. Analog computers are actually a great way to become introduced to differential equations because they give a more intuitive understanding of the concepts of differential equations. And the differential equations I'll be demonstrating in this video are going to be very simple. I'll start with the inputs to the analog computer. Parameters are entered into the analog computer via potentiometers. Potentiometers are basically variable resistors whose output is a variable voltage. This is similar to the volume control on a stereo. So as you turn the knob clockwise, you're actually turning, in the old days, a potentiometer. Modern stereos might use a rotary encoder. But the concept is the voltage on the output of the potentiometer will change, and that will affect the volume of the audio coming out of the stereo. In the case of the analog computer, the output of the wiper arm will generally be the input to one of the computing elements, and it represents a coefficient or a parameter of the problem. On the GP-6, the potentiometers are actually labeled coefficient potentiometers, and that's because they're typically used to set up the coefficients of differential equations or any type of equation that you'd like to put into the analog computer. Once you perform the preliminary steps of solving the problem, each term of the problem will have a coefficient that could be set by a coefficient potentiometer. With the type of problems you'll typically try to solve with an analog computer, the sign of the output voltage is determined by the problem, so you really only need either a positive coefficient voltage or a negative voltage. In the Comdyna GP-6, there are 8 coefficient potentiometers. 6 of these are single-ended, so they're 1 through 6 up here on the controls, and in the layout of the patch panel, they're represented by these jacks here, labeled 1 through 6. If you'll note, these only have 2 connections, one for the upper side of the potentiometer and one for the output of the potentiometer, which is typically called the wiper arm. The lower side of the potentiometer is actually tied to ground. There are 2 potentiometers, 7 and 8 here, which have open top and bottom terminals, so you could actually connect to different voltages, and particularly a voltage other than ground, to the bottom potentiometer, so the output of that potentiometer can vary below ground if necessary. For most problems in an analog computer, you would typically use the single-ended potentiometers because the nature of the problem will define the sign of the coefficient, so those are adequate. But for the demonstration I'll do in this video, I'll actually use the dual-ended potentiometers so we can more easily see what happens when you vary these voltages through the entire range of the analog computer. So I'll go ahead and set up the potentiometers right now, and it's just done with these jumper wires. I'll go from the positive reference to the upper leg of potentiometer 7, and then from the negative reference to the lower legs. So the references are actually plus and minus 10 volts, so the output of that potentiometer will be able to vary all the way from minus 10 to plus 10. And then the same thing on 8. We'll go from the upper side of 8 to the positive terminal, and the lower side of 8 to the negative terminal, and I can just stack these jumper wires. Now the differential equation I plan to demonstrate is the simplest one I could think of, and I will call it a differential equation. I guess it could be argued it wouldn't even show up in a textbook for differential equations. But the differential equations I will solve is dy over dt equals m. And don't let the terminology worry you if you're not familiar with calculus or differential equations, but that's an interesting differential equation in my view. I guess the term of the actual dependent variable would be the 0th power, so there is the dependent variable doesn't show up, but its derivative does. And the interesting thing to me about that differential equation is it sort of highlights what the derivative is. The derivative of y with respect to t, which is dy dt, equals m. And we all know from algebra that m typically represents the slope. So that highlights the fact that the derivative is the slope. So if you were going to solve that differential equation, as simple as it is, it could be solved by a separation of variables. So you start with dy over dt equals m, and then you multiply effectively both sides by dt, so then you have dy equals m times dt. Then you can integrate both sides. Effectively, you're integrating 1 with respect to y, and then you're integrating m with respect to t. So what you end up with is y, because the integral of a constant 1 is the actual variable, y equals m times t. But in calculus, we know that anytime you perform an integration, you need a constant of integration, which is typically labeled c, but in this case, I'll label it b. And that's because now we have the solution to this differential equation is actually y equals mt plus b. And in basic algebra, we learned that y equals mx plus b. Well, here the dependent variable is just t, because typically the types of problems we're solving are physics problems, and the independent variable is usually time, so we use t. So now the differential equation we're going to solve is simply dy dt equals m, and the solution will be y equals m times t plus b. So the way we enter that differential equation into the analog computer is we generate the variables of interest, and in this case we have a way to integrate the actual dy dt equals m directly. So basically we will input the value of potentiometer 7 into this integrator, and it can integrate directly, which is a very useful feature. So we'll go ahead and connect that input to the first input of integrator number 1, and then we'll use the second potentiometer 8 in this case, to enter the constant of integration. So we go from the wiper of 8 up to what we refer to as the initial condition jack of integrator 1. So integrator 1 will always start with this value, and at the output this will effectively be the y-intercept of the solution. So that's all there is to solving that differential equation. Now, an interesting fact of the analog computer is that all of these computing elements also invert their output. That's just the nature of the amplifiers in an analog computer. So to make things easier, I'll take the output of integrator 1 and apply that to the input of this inverting amplifier, which simply re-inverts the output. So on the output of amplifier 7, we'll have the true output. And then one final part of the setup I want to do is I will just disable integrator number 2, because we won't be using that one, and if I don't disable it, we may see some overloads. The other half of the setup here that's already configured and is a little bit complex, I will use in the demonstration of the computer outputs. I won't go into those in detail, but I will cover that solution in a later video. Now with the computer set up, we can take a look at the solution to our simple differential equations, dy dt equals m. I'll go ahead and turn up the intensity on the oscilloscope. And we don't seem to have much of a trace here. We just have a line going straight across the oscilloscope, so it looks like a typically grounded oscilloscope output. But that's actually the solution to this problem, because in this case I have a slope of 0 and a y-intercept of 0. I'll get into this in more detail when we talk about the output of the analog computer, but on the oscilloscope, t equals 0 is actually over here. It's sometimes a little confusing even to me because you have a cross grid just for convenience on the oscilloscope, but the 0 is not here like on a typical piece of graph paper. T equals 0 is over here. And that's basically because in solving problems with the analog computer, we're only interested in positive time. We start the solution at t equals 0, and we don't really care what happened at times before 0. So there's no need to have a 0 point here. And then on the y-axis, we basically have minus 10 volts to plus 10 volts excursion here, and that's another part that makes this a little confusing with a modern oscilloscope, because the grid references, there's only 8 grids in the y-axis, but there are 10 grids in the x, or actually t-axis. So that gets a little confusing, and even confuses me at times. But we can take a look. Another aspect of the coefficient potentiometers is we can actually look at their values. So we set the mode selector to pot set, and then on this, this is which pot we're looking at. So on pot 7, it's set to 0, and pot 8 is also set to 0. So when we go to operate mode, we basically have a line with 0 slope and also with a y-intercept of 0. And that would be just a flat line crossing the y-axis at the point 0. So now we can actually introduce a slope of m here with potentiometer 7, that's on the very input of the integrator, and we can adjust the slope of the line. And because I set this problem up using the two-ended potentiometers, we can actually apply a negative slope as well as a positive slope. And then this is where we were in the beginning with 0. So if I set the slope at that point, we should have a slope of approximately 1, because we have 1, 2, 3, 4, 5 to the center point, and then this is 2 divisions, or halfway up, so that would be 5 on the y-axis. So let's go ahead and look at the, and in fact the potentiometer 7 is set to 5, or excuse me, potentiometer 7 is equal to 1, so that is setting our slope. Now, if I move potentiometer 8, that will adjust our y-intercept. So I can set that to 2 divisions down, should be about 5, and then we go to pot set here, and now we have to switch over to there, and I missed it by a little bit, but it's pretty close to 5 there, and actually it's negative 5, so we can crank that up just a hair, and if we want, we can set it to 5 pretty precisely, close enough. So with that, we have a fairly wide range of control we can apply to our problem. Now, an interesting part of the analog computer is, as I mentioned, the reference voltages are from minus 10 to plus 10. If I increase the slope too far, you notice the overload light comes on, and that's because we're exceeding the maximum range of the analog computer. Now, at first glance, you might think that makes the analog computer somewhat limited in its use, because you would think it could only solve a problem with parameters from -10 to +10, but that's where scaling comes in. This is very similar to how a slide rule works. When you solve a problem on a slide rule, you really only have numbers from 1 to 10, if I recall properly. But the key is you can mentally move the decimal point wherever you want. So that's a simple form of scaling. In the analog computer, scaling is a little more complicated because in some cases, if you just used a factor of 10 scaling, your problem would either be too large or too small, and that either one of those conditions can cause a problem. If it's too large, your amplifiers will overload and your problem will not be correct. If it's too small, you'll be operating in the noise range of the amplifier, and that will also have a chance to introduce an error. So generally you want to keep the solutions and all of the variables in as close to the mid-range as possible, I guess would be a simple way to say it. So the scaling factors that come into play are sometimes a little bit complicated to calculate. So that covers the input side of the analog computer. There may be some subtleties that I'll get into in future videos as I solve more complicated problems with it. Now we'll take a quick look at the oscilloscope a little bit closer so we can see the effect of adjusting potentiometers 7 and 8. This gives us a little closer view of the oscilloscope as I adjust the coefficient potentiometers. So as I discussed, as I adjust potentiometer 7, we see the slope of the line changes. So that could be considered M of the y equals mx plus b. And then as I adjust potentiometer 8, the y-intercept changes. And we can go, as you see here, I'm already in the overload range. So I would need to bring the slope down to get an accurate output from the analog computer. But we have a full range of control on either parameter. I can go with a negative slope, a zero slope, and then the y-intercept could be adjusted to any point within the with the -10 to +10 volt range. Now the slope, of course, I can't go very high, or it doesn't do me much good to go very high with that because the amplifiers go into overload fairly quickly. So if I had a problem with that high of a slope, I would need to scale the problem in order to get accurate results out of the analog computer. But I think that's a good demonstration of what I would call the simplest differential equation imaginable. We'll move on to the output section next. Next, we'll take a look at the basic outputs of an analog computer. With most analog computers, there are basically two types of output. One is the voltmeter, which gives you a fixed reading of any output, and then the other is the oscilloscope. Now, with the Comdyna GP-6, you would typically use a standard, general purpose oscilloscope with this. You could use a digital oscilloscope, but for these purposes, I prefer to use an analog oscilloscope. But it's used in a little bit different mode than a typical oscilloscope, as we'll see. But first of all, we'll talk about the simpler output, which is the voltmeter, I should say. It's not a multimeter. As you see, the voltage is varying on the voltmeter, and that's because I'm running in what's called repetitive operation mode. I do that because that gives us a quick update of the oscilloscope. So typically when you're analyzing a problem with the oscilloscope, you can get immediate results in the repetitive operation mode. But the normal operation mode might be considered just the operate mode, where we initiate the analog computer to its initial condition, and that's actually adjustable, as we saw earlier, by the potentiometer 8, because it's plugged into the initial conditions. So as we talked about in this very basic differential equation, that would be considered the constant of integration. Then when we run in operate mode, that runs it in a very slow mode so we can actually observe the problem as it moves across. And you could actually use this hold mode to stop the problem at any time. And then you get an actual value of the output of the analog computer at that instant in time. And you could plot, you could record that off of the oscilloscope by measuring the time across the x-axis and the vertical displacement in the y-axis, and then calculating that against the range. So then we can continue the operation until we're finished, and then if we wanted to do another run, we could go back to the initial conditions and I'll set for a different slope of 7.5 or so, and then operate, and you see we start off at a lower point with the same slope. And again, we can hold that at any point throughout the range. And then if I change the slope in this mode, I can't see until I actually run it what the slope is doing there. So there we see the slope was so low and in the negative direction that we went off the screen, and now we're in overload there. So we can go back to the initial condition. Now another thing the meter could be used for is to set up the potentiometers for operation. So we go to pot set mode, and then I can set the pots for the value that I want to run. So I'll go ahead and set a +1 slope, and we'll go ahead and look at the y-intercept, which is the initial condition pot of 8, so we'll go ahead and leave that at 0 there, but I can adjust that and see what the exact value is to set up my problem. Then we switch back to the amplifier that we're interested in looking at the output, which is actually amplifier 7, and switch over to operate mode, and now we're at that initial condition of 0, and with a slope of 1 I would expect it to hit 5 when t equals 5, and then hit 10 at the end of the operation. So we'll go ahead and hit the operate key, and then you can stop it at any point, and that's one of the nice things with the analog computers. You can freeze for a pretty good amount of time, and it will hold the existing value while you log the data. Then we can continue with the run and let it finish out. Now, if you just continue to let it run, I'll stop it there, but if I continue to let it run, it'll eventually go into overload mode, so we can just switch it back to the initial condition there. So that is the basic function of the meter output. Go ahead and do one more run. As you can see, it just follows the output in time. Now it's a little difficult to read as it's moving along, and then you can just hold it at any time and log down a particular value. The more complicated output is the oscilloscope output. Now, back when analog computers were in use, the oscilloscope was actually an integral part of the analog computer, and I've seen some of the advertisements for that. They would have a dedicated oscilloscope which had a much larger screen, and I would assume it had a proper scale, so the scales would be the same in the x and y axis, which might make your calculations easier. But in this case, with the Comdyna GP-6, it just uses a general purpose oscilloscope, which of course makes the computer much less expensive. But it's a little bit tricky to understand, especially if you're not really very familiar with oscilloscopes. The oscilloscope is actually operating in XY mode. So the Comdyna GP-6 will generate a sweep for the time axis that is actually calibrated in what they refer to as computer time. And that's the time related to your problem. And then it generates the Y output based on whatever amplifier you have selected. So you are plotting in XY mode on the oscilloscope the computer time across the x-axis and the value of the output of a particular computing element on the y-axis. And that makes it a little bit complicated, and there is a little bit of setup involved. In order to set up the oscilloscope, you need first, and I'll show you the XY mode on the oscilloscope later, but the key is to set these two dress pots to, you start with both of those on ground, and it's a little bit tricky. We want to adjust the horizontal position will actually determine where the dot is centered on the oscilloscope screen, so that calibrates the X zero position or X ground position. The Y ground position is adjusted with the actual second channel position knob here. So I've got those adjusted fairly well, but we'll go ahead and show you that. So that's how you would adjust there and there. And I may have a little parallax error because I'm not looking directly at the screen. Then we can switch this knob to the negative reference range and positive reference range. And if those are off, for the y-axis, we would adjust the Y calibration. So right now, the scope is technically not calibrated to measure volts, but what I'm doing is I'm calibrating it against the reference voltage of the analog computer, so it will give accurate results as far as the output of the analog computer is concerned. And then you want to check both sides and basically find the best adjustment for both the positive negative excursion and ground or 0 volts. Sometimes that's a little tricky, and there's internal calibration of the analog computer as well as calibration of the scope that may come into play there, but I think I have a pretty good setup here. And the same thing for the the x-axis or time axis. We can see that's pretty well at 0, and there, or sorry, at -10. There, if it was off, I would adjust the channel 1 calibration because that drives the x-axis. And then, sorry, I went to the Y switch. Same thing on the other side. So those you might have to go back and forth and adjust those in, but once you have the maximum excursion and the ground set calibrated, you can actually read off the individual time parameters off of the x-axis of the scope. Now, I have another problem set up here, which is just the basic physics problem of a spring mass damping system. So we'll take a look at that. I'll switch this selector back to computer time and then switch to repetitive operation, and we can see the typical spring mass damp. So you've got an oscillatory behavior with the damping in an exponential damping there at a certain frequency. Well, so that's how it would normally be displayed on the scope, but if we look at the scope in normal, what we call YT mode, and then look at both channels, you'll see what the actual analog computer is outputting there. And then what I'll have to do is I'll go ahead and set these both back to calibrated and reduce that. So here the sweep is a little slow. I'll bump up the intensity a little bit so you can see that a little better. But channel 1 is actually looking at that internally generated sweep signal, which represents the computer time. So that's just a linear ramp from effectively -10 to +10 volts. But then the y-axis is the actual problem solution, or the output of the analog computer. And you see they're both synced up to start at the same time. There's a little bit of a delay between the end of one solution and the beginning of the other, which is just the time for the sweep to sweep back, basically, and for the initial conditions to stabilize. But that's actually what is being inputted into the oscilloscope. But the way we look at it in the oscilloscope is to use this signal to deflect the y-axis across. So that's input into the channel 1, sorry, I said y-axis, the x-axis across, or the time axis. And that is channel 1, or x, in x mode. And then channel 2 is going to be what we use for the y-axis deflection. So that's what the raw signals that the oscilloscope is looking at. And then when we actually set these to XY mode, we really have our solution there, but we don't want to look at channel 1, and because I rearranged the sensitivity of the channels, we'll have to recalibrate. So before I go to recalibrate, I'll switch over to the zoomed in image of the scope so you can see that a little more clearly. But basically I'll just be resetting these XY address to look at the ground plus reference and minus reference on both sides, and you'll see the calibration procedure. So right now, because I took a look at those individual signals, we are out of calibration, and this will be a good demonstration of how to get the oscilloscope in calibration. So now we have the zoomed in view of the oscilloscope, so we can take a closer look at adjusting that calibration. So first of all, I'll switch the Y address down to the ground or 0 position, and the X address back down to ground. So now you can see our ground is way off because of the adjustments I made earlier. Now the scope is a little bright for this, so I'll kind of reduce the intensity of the dot there. And then we have to, we'll probably have to adjust both the voltage and the positions, but the horizontal position is just adjusted with the actual horizontal sweep position control, and then the vertical position is adjusted with the channel 2 position control. So that actually sets the 0, and to my eye that looks pretty good. So then we'll take the Y pot address and go to the negative reference, and that's pretty far off, so let's see if I can adjust that with calibration. Well, so what I did is I just took the calibrated or variable portion of the second channel, which is controlling the Y, out of the cal detent, and that only goes up from there. So I have to increase the vertical sensitivity effectively. So now I can actually bring that to the point at the bottom of the scope there. So that'll be our minus 10 volt signal, and that looks pretty good. Then we'll, oh, sorry, wrong switch. Switch over to the positive reference, and I don't see my dot, so that means I'm most likely off of the screen. There it is. I just brought that variable control of the second channel down a little bit, and that's the tricky part of this adjustment, is finding that happy medium. And usually if one of the excursions is pretty far off, I go back to the 0 position and reset the position of that channel. And let's see. So it's an iterative process, but I'll go ahead and call that. It's a little bit off at the bottom there, but we'll call that close enough. And then we go to the, what is for the computer purposes is the t-axis, but that's the x address. And the same thing, when I go to the negative one, we're well off of the edge there, so I can tweak the variable portion of that channel, and I'm not going far enough to reach that, so I need to modify the sensitivity a little bit. And the same process, we go ahead and set that, and we switch to the other side. There. And then this, what's a little unusual here is you got to remember when you're adjusting the x-axis, you actually use the oscilloscope horizontal position, not channel 1 position. So that looks pretty good. So that's the calibration process in pretty close detail. So now when we switch back to time, which is computer time on the x-axis, we can go back, and there was our original y equals mx plus b output. And then here is the spring mass damping output. And in this solution, I have the initial condition set to potentiometer 5, so I can actually adjust where that starts. And then this would be the, that appears to be the damping. And it's, you know, I have to kind of look at the problem. You can see it's not getting quite as high of an excursion, but the frequency is staying basically the same. But we can adjust that, and that will be more clear in a later video when I delve into that problem in a little more detail. We'll switch back to the full view here. So here is the output of the spring mass damp system again with the full system in view. And we can adjust some of these. I have to go back and rethink what the problem was here, but this pot here is basically affecting the frequency, so I think that has something to do with the spring constant there. And then the I think 3 it may be the mass, but I'll have to take a look at that. And then these 5 and 6 are the actual initial conditions for the velocity, so you could actually impart a little bit of velocity and the actual position that the mass starts in. But that's a problem I'll take a look at in more detail in a later video. The computer also has a way to basically adjust the actual time of the computer. Now I'm getting an overload there, and that's most likely because of the slope on the first channel, but we'll go ahead and take a look at this solution again. So we can actually speed up computer time. So if you have a problem, say like this one, that is actually taking more than 10 seconds to settle out, you could actually adjust the computer time to let the problem run through much more time and get values further out in time on the display there. And then another way to adjust that is by adjusting the actual parameters in the problem to scale for time. But on the Comdyna GP-6, they give you a way to control the time parameter of the computer, so to speak, directly. So I think that covers the basic inputs and outputs. This was not a real in-depth video, but I just wanted to cover some of those subjects before I get into solving some more detailed problems. So it might, hopefully, will make a little more sense with what I'm doing when I'm solving the problem, because it's time-consuming to describe this in detail on every problem that's solved, but you get an idea of the overall inputs and outputs of the analog computer. So I hope you found that useful, and thank you for watching.